this video we're going to be going over some conduction calculations. So we're going to be using these two equations to calculate heat transferred and the resistance. Here we have the heat flux, which is the heat transferred per unit area, which we're going to apply to an example. So for the first one, calculate the heat transferred if the thermal conductivity is 54. We have T1 as 300 Celsius and T2 as 250 Celsius. So to calculate heat transferred, we're going to be using these two equations. If we substitute in the values that we already know, so delta T is just the change in temperature, so the difference between T1 and T2. So that would be 300 minus 250. Because it's difference, as in changing, we don't need to calculate these in Kelvin, because the difference in Kelvin would be the same as the difference in Celsius. And then we have resistance at the bottom. Then we calculate resistance from X, which is the thickness. So 0.05. These numbers are all in SI, so they'll be meters. So we have X over A, which is the area, so it'll be 1.2 multiplied by 1.8. And then multiplied by the thermal conductivity, which we're given in SI units as 54. Then we can put all that in a calculator and calculate the resistance. So we have 4.29 times 10 to the minus 4. And now that we have the resistance, we can put it into this equation to calculate the heat transferred. So we have Q equals 300 minus 250, which is 50, but we'll just keep it that way. 4.29 times 10 to the minus 4. We have 300. And that gives us an answer of 116,640. And that will be in watts, which is joules per second. And that's the heat transferred for this example. For the next example, it's a little bit more complicated because we have multiple systems, i.e. the heat goes from here to here through 3 composite walls. And so we're asked to calculate the heat flux, and we're given the temperature going in and the temperature coming out. So with all of these examples, we're going to assume there's insulation around here, so heat is only lost through coming in and coming out. So for this one, we're going to start off with these equations. So we know that the heat flux is equal to the heat transferred per unit area. We know the heat transferred is delta T over resistance, and resistance is the thickness over the area multiplied by thermal conductivity. So we're asked to calculate the heat flux, which is this. So the heat flux is heat transferred divided by area. So if we divide both sides by area, we'll have heat flux on this side. So we know Q is Q over A. So if we divide this side by A and this side by A, we have delta T divided by A times resistance. And we of course know the formula for resistance. So if we add in the formula for resistance, we have Q equals delta T. Now we have A, because we have composite walls, i.e. we have them going through each other, we'll just be adding the resistances, so it'll be thickness of wall 1 plus thickness of wall 2, and so on. And so because they're timesed, we have x1 over area 1, which is what we have here. Because we've got 3 walls, 1, 2, 3. And now if you see here, we have A on the top and A on the bottom, i.e. A is multiplied and A is divided, and this is constant through all of the walls, so we can cancel out. So we're actually left with this equation. Heat flux equals delta T over thickness divided by thermal conductivity. And that's the same for each wall. So then we look at our diagram and we're given all of those values. Again, these values are all in SI units. So if we substitute in delta T is 1250 minus 64, and then we have the thickness divided by the thermal conductivity, and same goes with the other 2 walls. If we put that in our calculator, we should get the heat flux. That gives us 1467.46. So that would be watts per meter squared, because it's heat transferred per unit area. So that's why you have the meters squared, but it's divided by. So it's per unit area. If we do another example, this time involving cylindrical systems, the equation for heat transferred is the same, i.e. the one with the temperature difference and the resistance, but because the heat transfer changes with the radius of the cylinder, a different equation is used to calculate the resistance, which involves the natural logarithm and the radii of the cylinder. So if we do this example, wants us to calculate the heat transferred. We're given the inner and outer diameter, and we have 2 temperatures, the length of the cylinder and the thermal conductivity of the cylinder. So if we plug in the numbers, we have Q equals the temperature difference, which is 60 minus 55, divided by R, which is the resistance, which we're going to calculate from the next equation. So resistance equals ln, so we have radius 2, which is the outer radius. Here we have 0.3 as the outer diameter, so the outer radius is 0.15, and then we're dividing it by the inner radius, so 0.1. Then we divide by 2, multiplied by pi, multiplied by the thermal conductivity, multiplied by the length, which is 40. So if we calculate that, the resistance is 3.59 times 10 to the negative 5. Then if we put that into this equation we have here, so we have Q equals 60 minus 55 divided by 3.59 times 10 to the negative 5. The heat transferred is 1394 466.18, and that will be watts, joules per second. And that's it.